Hello. Okay. Yeah, in fact, a lot of what we're covering today is stuff is very should be very familiar if you remember Data 100, and if you don't, well, you're going to remember this stuff now, hopefully. Okay, so just to double check, mic is working, audio is good? Okay, lovely. So let's get into it. So first and foremost, some of you may now currently be thinking, Marvin seems to have gotten shorter and a lot more tan all of a sudden. The conspiracy theorists among you might think this is not in fact Marvin. This time you're correct. So who am I? My name is Ishan Srivastav. I'm one of your head TAs for this semester. I've interacted with, at least a couple of you in office hours, PRs, discussion, and so forth. And I'm going to be giving today's lecture because Marvin has graciously agreed to let me. And so today we're going to basically be talking about evaluating classifiers, and a lot of the relevant terminology from today is like precision, recall, ROC curves. A lot of what we're doing today should be familiar from Data 100, which most of you, if not all of you, have already taken. So let's get into it. So I want to remind us of what we've already covered this week. So on Monday in lecture 17, the title was Evaluating Learned Models. The question we were broadly answering was how do we decide what combination of model parameters and hyperparameters is optimal, right? Do we just go off what's best on the training set? If we're not going off that, what should we look at instead? And so some of the key terms you learned there were like risk, empirical risk minimization, and cross-validation. And so of those terms, cross-validation is the most pertinent to today's lecture. And so to give you a very quick recap of what actually goes on in cross-validation, if we're doing k-fold cross-validation, you basically divide your data into a bunch of k folds. You train your data on k-1 folds. You validate it on the kth fold using some metric. And then you kind of do this for all the different ways you can have k-1 folds and k folds divvied up. You average across all these possible folds, and you go with the model or like the choice of parameters and hyperparameters such that they have the best validated metric on average, right? That's the gist of what goes on in cross-validation. In lecture 18, we were doing bias variance and decision theory. And so the overarching question was, for classification, how does the problem setting affect the decision rule and the generalization error, right? And so something that Marvin showed you on Wednesday is that the Bayes optimal decision rule does not always minimize loss. Can someone tell me why that might be the case? In the front? Exactly, right? So the specific example given is cancer detection. And the more general principle is if you have asymmetric loss functions, so when you make incorrect predictions, so predicting 0 and then getting 1, if the loss is different than if you predict 1 and you get 0, so if you have this asymmetric loss function, especially for incorrect decisions, that is an example of when Bayes' optimal decision rule does not always minimize loss. And that kind of idea of thinking about asymmetric loss functions is going to be relevant to today's lecture a fair bit. So cross-validation and asymmetric losses are arguably the two most important things from this week's lectures to focus on, and most of other things are relatively self-contained. So today's lecture, the overarching question we're asking ourselves is, we've made progress in evaluating models in the context of like regression, but how do we evaluate classifiers, right? So we're going to see why we can't do exactly what we've already been doing in the context of like evaluating regression models, and how we can apply similar but not identical steps to figuring out what to do in the case of evaluating classifiers. And the buzzword for today's lecture is more or less metrics. So we're going to talk about a bunch of different metrics and how they kind of relate to our classification problem. And so a lot of the metrics we're going to discuss are precision, recall, sensitivity, specificity, so on and so forth. I'm going to talk about ROC curves, which again, you should have seen in 100. And if I have time, I will go over an interview question related to today's content. So now, an incentive for paying attention beyond, just loving to learn and maybe wanting to get a good grade is that the content from today's lecture has shown up in the majority of data scientist interviews I've given. So if you need any more incentive to pay attention to what I'm saying, that's what I got for you. And if we do well enough that we get through the whole lecture, I will tell you a question I got in one of my interviews and how I answered it. I got the job offer, so I think I did reasonably well. So hopefully we'll get around to that. Okay, so let's start off with a naive evaluation of classifiers. Let's just say that we have 5 labels that we're looking at, and we have 2 probabilistic classifiers. And the fact that probabilistic is important, so bear that in mind. So let's just say we have a logistic regression model, and we have a neural network model, right? So as you can see, in the first case, or actually these are just a bunch of predicted probabilities, we can see what the true label is. Now remember that it's not a classifier just because you have a model that outputs a probability. You also need a decision rule. So let's say our decision rule is that if the predicted probability is greater than or equal to 0.5, we classify it as class 1. Otherwise, we classify it as class 0, right? Let's just pretend that's our decision rule for now. And let's look at accuracy. So over here, you'll see that both models have the same accuracy. Both models have an accuracy of 0.8 or 80%. In particular, if you look at the second example over here, the logistic regression using our decision rule predicted to be class 1, when in actuality it should be class 0, which the neural network correctly predicts. In comparison, if you look at the third example, then the logistic regression is correct in that it predicts probability greater than 0.5, so it correctly predicts that, but the neural network predicts as class 0 because the probability is less than 0.5. So they have the same accuracy, but does that mean both models are equally suited to the task at hand? And with the information I've given you, the correct answer is I don't know, because I need more information. For example, we see that in one case, one model is predicting 0 and should be predicting 1. In comparison, the other model is predicting 1 and should be predicting 0. And the other cases, they get correct, right? So now, to figure out which model we'd actually want to go with, there are a couple of different ways to look at it. And so this is a very brief, motivating example of the question we are trying to answer today when I say we're talking about evaluating classifiers. So let's talk about, and so over here, we have our probabilities, right? But we don't always have probabilistic classifiers. Like we see in SVMs, you have a decision boundary, and your decision rule is more or just less what side of the boundary you're on. So we can't just compare in SVM to logistic regression model by looking at probabilities, because in the case of the SVM, we don't actually have probabilities, right? So can we compare losses? So is it meaningful to compare losses across different models, right? So for logistic regression, you have your cross-entropy loss. And then in SVMs, as Marvin has shown you already, SVMs are basically just optimization problems you solve for, right? So now does it make sense to compare what we get when we have our cross-entropy loss in logistic regression versus the optimization problem that we see in SVMs? And the answer is no, right? They're apples and oranges in the sense you can't compare different loss functions compared to each other, right? Just because if I had 2 loss functions and one model trained on one loss function has a lower value of that loss function compared to the other model trained on some other loss function, that doesn't make the first model any better, right? It's not meaningful to compare them. If they had the same loss function, you could look at that. But even if loss functions are comparable, we should be evaluating the actual decisions made by models, not the loss functions. We do this using metrics. So before I get into metrics, when I say we should be evaluating the actual decisions made by models, not the loss functions, I mean that, as I said, it's a classifier once you have a model and a decision rule, right? So even if you have comparable loss functions, or the same loss function, and you have a model that has lower loss, that doesn't necessarily make it a better model until you put it in the context of specific decision rules and then evaluating the decisions made by those respective models. And so, like I said, the buzzword today is metrics. We're going to use metrics to actually characterize and evaluate decisions made by models. So the first metric is accuracy. We already touched upon it in the previous slide. I feel like accuracy is a pretty straightforward metric, not a lot to explain there. You look at the number of predictions you made correctly divided by all the predictions you made at all, right? It's just it's a proportion of all the correct predictions you made. Any suggestions on when you don't want to use accuracy? At the back? Right, so similar to the example mentioned earlier, if you're doing cancer detection or let's just say on some medical application, for example, a false negative or a false positive aren't the same as each other, right? So you don't want to use it when one class has like a different penalty compared to the other class when it comes to misclassifying them. And also in terms of class imbalance, right? Because if I have like 99% people in one class and 1% people in the other, I could always just classify them as belonging to the first class, and my accuracy would be 99%. But my model would not actually be doing anything useful, right? So those are the two main reasons. If we have class imbalances, and if we have, let's say, asymmetric loss functions. We'll see specific examples of that later on, but we've also already covered them in the sense of like medical applications, or like so cancer, COVID, so on and so forth. So we want to look at metrics that aren't just accuracy, right? And so you don't just want to look at accuracy, we don't just want to look at like loss functions when it comes to evaluating classifiers. So this is a very basic motivating example where we kind of have like concrete data to look at. So over here we have a bunch of data points. So over here the positive class are these red pluses, and the negative class are these blue negatives, okay? And so over here, let's say the quote-unquote x-axis, you can look at it two different ways. Either we just have a probability, in which case this is from 0 to 1, and we're predicting the probability, our model is predicting the probability that belongs to class 1. Or you can even think of this as feature space, where this is our x-axis, and this is just like one-dimensional data, and this is what we're looking at. And so for what I'm going to do in this example, it doesn't really matter which perspective you have, but in this particular case, you can use both of them. So either way, this is our decision boundary. So everything to the right of the decision boundary over here gets classified as positive. In comparison, everything to the left of the decision boundary gets classified as negative. Right? So that is the gist of what we're doing. So just bear this example in mind. We'll come back to it in a second, right? So I want to actually define let's say, the building blocks that we're going to use to build up the actual metrics. And before I do that, the two heads up I want to give you are that, one, we're only going to talk about binary classification. At least some of these metrics generalize to multi-class easily enough. But a lot of these definitions aren't really going to change. But for simplicity's sake, we'll talk about only binary classification today. Part two, positive and negative can be arbitrary labels. Like if we're detecting COVID, for example, it's pretty clear that it makes a lot of sense to me at least that COVID positive is class 1, COVID negative is class 0. But there are cases where the labels can be a little more arbitrary. Like if I was doing a classification between like two species, like trout versus salmon, it doesn't really make sense which one is 1, which one's 0. But almost everything we do today does not require 0 and 1 being meaningful or like sensical labels, as long as they're just two different labels that we work with. So don't worry about if you can't think of, what should be negative, what should be positive. So after that, we can actually get into the building blocks, like I said. True positive, hopefully easy enough to understand. You predict 1, and it's actually 1. Similarly, true negative, you predict 0, it's actually 0. False positive, you predict 1, and it's actually 0. Also known as the type 1 error in like statistical terminology. And then false negatives are when you predict 0, but it's actually 1. Also known as type 2 error. So I'm assuming that remembering true positives and true negatives isn't particularly difficult, but false positive, false negatives can give you at least a moment's pause. And so my tip for remembering this is that the second word, or like the N or the P, positive, negative, tells you the decision the classifier made, while in comparison, the true or false tells you how reality corresponds to the decision. So to give you a particular example, let's look at false positives, right? It's dash positive, that means our model predicted 1, and it's false, so that means the actuality is the opposite of positive, so it's class 0. So that's how I remember it. You're obviously not obligated to remember it that way, but hopefully this helps. One thing I will say is that this stuff you should actually be able to memorize, in that theoretically, you could put this on the cheat sheet for the midterm, but you can't do that for interviews. And so a lot of what we cover today, like the definitions, the metrics, it is useful to be able to memorize these so you can like talk coherently about them in conversation without having to refer to an additional or external resource. So confusion matrix is not, in fact, when you fail your 54 midterm. It is when you look at the different ways you can evaluate decisions, right? So the diagonal terms are your true negatives and your true positives. And so in our convention, we have the actual labels as, let's say, the rows, and the predicted ones as our columns, right? So negative, negative means that, you predicted negative, it's actually negative, so by definition, it's a true negative. In comparison, over here, you predicted positive, but it's negative, right? So it's actually a false positive. And so over here, negative means 0, positive means 1, if you go back to our earlier example, right? And so like I said, there's a type 1 error, and the similar idea for false negatives and true positives. One thing I'll point out is in that our convention, the actual labels we're using represent the rows of our confusion matrix, but some people might want to use the columns instead, and then they'd use the predicted as the rows. They're just two different conventions. It's not necessarily a big deal, but whenever you see a confusion matrix or you're creating one, just make sure you know which one you're using as which. And as long as it's clearly labeled, you're pretty much fine either way. So now we've actually talked about, let's say, our building blocks, defining true positive, true negative, false negative. So we can go back to actually discussing metrics, which are generally at least some combination of these terms. And so the first metric, like we said, is accuracy, right? And so using the building blocks we discussed earlier, it's basically true positives plus true negatives divided by all the predictions we're making, which is by definition, true positive plus true negative plus false positive plus false negative, right? So what proportion of our observations do we classify correctly? In comparison, and the next metric is precision. The precision is the ratio proportion of true positives compared to the sum of true positives and false positives. So what proportions of observations that we classify as 1 are actually 1? Denominator depends on the model, right? So if something has high precision, it basically means that if I'm classifying something as 1, there's a pretty good chance it actually is 1, right? In comparison, we have recall, which is true positive divided by true positive plus false negatives, right? So the numerator is the true positives, and the denominator is all the positives in the data. The contrast this to precision, where the denominator was all the positives in your model, right? So recall is basically what proportions of the ones in the data are we actually classifying as 1, right? So the denominator depends on the data compared to precision, where denominator depends on the model. So with recall, it's basically saying that if I belong to class 1 in the population, a model with high recall is generally going to predict that I belong to class 1, right? So tip number 2 for remembering is like the definition of precision. This is a trick I picked up from a fellow Data 100 TA, is that precision starts with a P. So every term in precision has a P in it. So it's true positives, false positives, right? So that helped me out, again, if whatever works for you. So those are our first metrics, right? We've already talked about accuracy. We've now officially introduced precision and recall. Our next set of metrics is sensitivity and specificity, right? So sensitivity is true positives divided by true positives plus false negatives. It's also known as the true positive rate, or TPR. It should look familiar. Why? Exactly, right? Sensitivity and recall are the same thing, as are also true positive rate, right? Remember, we're looking at the proportion of true positives compared to just all the positives in the data, not the positives made by our model, right? So it's the same as recall. In comparison, specificity is the true negative rate, right? So your numerator is the true negatives, but the denominator is all the negatives that exist in the data. And so that's going to be your true negatives and your false positives, right? Together, they comprise all the negatives that actually exist in the data. So how I remember sensitivity, specificity, is that sensitivity has an N in it, so you might think it's the true negative rate, but aha, it's actually the true positive rate. And then specificity has a P in it, so you might think it's the true positive rate, but aha, it's the true negative rate. So I think whoever came up with the names for Greenland and Iceland also came up with sensitivity specificity. They pulled a switcheroo on us, but hopefully after this, everyone here actually remembers what the correct names are. I hear someone chuckling. Oh, is that a question? Like slow it down, you said? Sure. So to slow it down, sensitivity specificity. Sensitivity is our true positive rate. When I say true positive rate, the proportion is out of all the positives that actually exist in the data, right? So that's why your denominator is true positives and false negatives. And then specificity is the true negative rate, right? So you look at the proportion of true negatives expressed as negatives in all the data, right? And so all the negatives in your data, meaning your true negatives and also your false positives, because by definition, false positives are when you predict one, but it's actually zero or the negative class. And so, as I've said over here, in both cases, the denominator depends on the data, not the model predictions. In other words, depends on the actual positives and actual negatives, right? Because the denominator for sensitivity, actual positives, the denominator for specificity, actual negatives. Any questions? Any other pieces of feedback beyond let's slow it down a little bit? No, I mean, it's a completely valid concern, so I want to be sure. Yes? Yes, don't you worry. Anything else? Okay, let's get into it. So I've given you what are arguably some of the most conventionally or like well-known metrics. Accuracy, obviously, but also precision, recall are very commonly used. Sensitivity, specificity, also very commonly used. Like if you see any paper about, let's say, for example, evaluating how COVID tests are, they'll probably talk about it in terms of sensitivity and specificity. That being said, there are many other useful metrics that we just don't have time to cover today's lecture and probably this semester, right? But they exist. So you have your F1 score, or you have your false discovery proportion, or your false discovery rate, so on and so forth. Pretty much every metric you see when you boil it down is going to be some combination of the 4 building blocks, right? When I say 4 building blocks, I mean your true positive, true negative, false positive, false negatives, right? So back to the motivating example we had earlier. And so again, just to remind you, you can think of this as your feature space or a predicted probability that it belongs to class 1. Whatever we're going to do next works fine either way. So anything to this side of the decision boundary to the right gets classified as positive. Anything to the left or left side of the boundary gets classified as negative, right? And so now, as an exercise for all of you, take 2 to 3 minutes and try computing the number of true positives, true negatives, false positives, false negatives, compute the building blocks, and if you have the time, try computing all these 4 terms without referring to previous resources, so just off your memory. And if you want to make it easier, then you can, in fact, refer to your resources. Yes? Yes, compute the number of true positives, true negatives, false positives, false negatives, and then all these other terms are ratios or proportions of some sort. So take about 3 to 5 minutes on that, and then we'll regroup and discuss. And you are both allowed and encouraged to talk to the people around you to do this. If you're done working on it, or either just don't want to work on it anymore, like look up so I can see how people are feeling. Okay, most of you are done in at least one sense of the word. Give it another minute and then we'll go through it together. Okay, let's get into it. So first things first, how many true positives do we have? And don't bother raising your hand, you can just shout the answer out. Yep. How do we know that? Because if you look at what we're classifying as positive, there are 5 that are actually positive, right? What about true negatives? How many do we have? 3, right? We have 3 blue negative signs in the region where we're classifying things as negative. How many false positives do we have? So yeah, what is a false positive? A false positive is when you predict class 1, but it's actually class 0, or class negative, which is this blue negative over here. So we have exactly 1 false positive. And how many false negatives do we have? 2, right? Because we have 2 examples over here that are positive but are getting classified as negative, which is the definition of a false negative, right? So now, because I've been going through this like I have a train to catch, we do actually have time to compute this. So precision, what do people get? And report as a fraction, not a decimal. 5/6, right? How'd you get that? Right, so that's the formula, and we've already computed what the terms are. And so another way of looking at this is that for precision, you just look at everything that's classified positive. So just ignore what's going on the left side of the decision boundary. You can see that of the 6 predictions we're making, 5 of them are correct, right? Or 5 of them are true positives. So our precision is going to be 5/6. What about recall? How'd you get that? Yep. So again, you can just plug in the formula. Another way to look at it is that there are 7 positives, of which 5 of them are being classified correctly, right? So 5/7. What sensitivity? Exactly. Sensitivity is the same as recall by definition, so we know it's going to be 5/7 as well. What's the specificity here? How'd you get that? Exactly, right? We have 4 negatives or 4 blue negative marks over here, of which we are correctly classifying 3 of them, so our specificity is 3/4. Motivating example number 3. This is a figure that you already saw in the previous lecture, so I've shamelessly ripped it off from Marvin's lecture, and it says that if time permits, identify which regions correspond to true positive, true negative, false positive, and false negative. So it's a similar idea as what we've already seen over here, but we're just building on it a little more. And over here, we're thinking about this in terms of like distributions rather than just like realizations of, or just observations or realizations of random variables. So spend about 2 to 3 minutes on this, and then we'll go through together. Oh, and I guess I should give you some background that this blue line is our decision boundary, and this purple distribution is our, let's say, the positive distribution of class 1. This yellow distribution is the 0 or our negative distribution, and anything to the right of the decision boundary gets classified as class 1. Anything to the left of the decision boundary gets classified as class 0, or the negative class. Okay, let's get back together. So does someone want to take a guess at what region we'd classify as like the true positive region? James? Yeah, so basically true positives means it's actually positive meaning belonging to this class and gets classified as positive meaning or like this purple distribution and to the right of the decision boundary, right? And so we're looking at the purple distribution, including this part to the right of the boundary where it overlaps with the other distribution. That's still part of our true positive region. And so for true negative region, it's the same idea. Now we're looking at the left of the decision boundary and we're looking at what all is in this yellow distribution, right? So again, it includes the overlap with the purple distribution that belongs to the left of the boundary, right? What about false positives? Yep. That's correct. And so again, false positives, you predict 1, but it's actually class 0, right? So look at your distribution 0 and see where it's getting classified as class 1. And that is exactly as mentioned earlier, the part of the yellow distribution that lies to the right of the decision boundary, right? And so false negatives, similarly, you look at the purple distribution, which is class 1, and you see where it's getting classified as class 0, which is this part of the purple distribution to the left of the decision boundary. And so, yeah, hint, hint, make sure you study this when you're preparing for the midterm. Okay, so we're going to take a bit of a pivot in that we're still talking about evaluating classifiers. We're now going to bring up ROC curves, and ROC curves are very much related to the metrics we've already discussed. But before we get into it, any conceptual things I can review? Any questions on what we've done so far? Yes? Good question. I don't know. But basically, you generally see precision and recall discussed in context with each other. And then you see sensitivity and specificity discussed in context with each other. And as to why you look at those pairings in particular, that one I actually can answer, and it shows up later on in the lecture. Yep. Other questions? Going once. Going twice. Okay, so ROC curves. As we've stated, a classifier is a combination of a model and decision rule. And in the case of probabilistic classifiers, we have a decision rule to convert probabilities into actual decisions, right? So for example, if you have a logistic regression model that predicts probability of 0.7, that's not a classifier yet. You need a rule saying that if the probability is greater than or equal to something, classified as class 1, otherwise classified as class 0, right? And so that means is that we have a model that always just outputs the probability, and then we can see what happens in terms of the decisions made as we tweak the threshold or the decision rule, right? So for what we can do is that for basically every number between 0 and 1, you can basically have a different probability threshold or different decision rule, and you can compute what the true positive rate or your sensitivity is, and you can compute the false positive rate. For context, false positive rate is false positives divided by false positives and true negatives. Like the denominator is again all the actual negatives in the data set. So it's 1 minus the true negative rate, or it's 1 minus specificity, right? So for all the different decision rules, you compute the sensitivity and 1 minus specificity. And then you can basically construct like a line or a curve through all these points. And that line or curve is known as a receiver operating characteristic, or ROC. You never need to worry about the fact that the full form is ROC, or is receiver operating characteristic. It's a remnant of World War II. The name does not make much sense right now, but that's a bit of trivia for you. So this is what ROC curves actually look like. And so this is from XKCD Comics. They're pretty funny. Anyway, like I said, the y-axis is the true positive rate, or your sensitivity. And the x-axis is your false positive rate, or 1 minus specificity. And so the perfect classifier is at this point. Can someone tell me why? What about that point makes it the perfect classifier? Yep. Right, so you have a true positive rate of 1 and a false positive rate of 0. So you have 0 false positives, and everything that's positive is, and you have no false negatives either. So you have like a true positive rate of 1, right? So that would be ideal. If you ever see this in the real world, that means something went wrong. You're never actually going to achieve this. But you can come relatively close, and these are examples of models, of different models and their ROC curves, right? And so over here, they've made it very clear that like this blue one is pretty much always better than this yellow one, which is always pretty much always better than this green one, which is better than this random classifier. And so a random classifier is basically a line of slope 1, and that is not a coincidence. Can someone tell me why the random classifier is basically just a line of slope 1? Yep. Yeah, like put in other words, that if you have a random classifier, your probability of being correct or like a true positive is 50%, probability of a false positive is also 50%. That's basically the gist of it, right? And so if you look at it like, basically it's saying that in the case of the random classifier, or actually with all classifiers, you kind of end up with this point over here where you have a true positive rate of 1 and a false positive rate of 1 as well, where if you're classifying everything as positive, that's what you'd end up with, right? Anything that's positive gets classified as positives, so you have true positive rate 1, and like all observations, right? So that is what happens at both ends of the ROC curve, right? So this is how you kind of visually evaluate classifiers, right? And so this is almost like a toy example where it's very clear which classifier you want to choose. Like obviously the blue one is the best of these, but there are ways of evaluating classifiers without just looking at them visually. So like quantitatively evaluating classifiers. And so if you want to quantitatively evaluate a classifier, you can basically summarize an ROC curve for a classifier by computing the area under the curve, also known as the AUC, right? And so the higher the AUC, the better the model. And as a fun fact, the AUC of a classifier is equivalent to the probability that the classifier will rank a randomly chosen positive sample higher than a randomly chosen negative sample, right? And so I want to give you examples of what AUCs actually look like. So again, this is an AUC of 100%. So like the best possible AUC you could get. And so the idea is that we always, like once again, we're kind of at this ideal point where you have a 100% true positive rate and then a 0% false positive rate. Then this is our random classifier, which has an AUC of 50%, which again is in line with the intuition that if you're randomly guessing, half the time you're going to be right, the other half the time you're not going to be right. And then you're not going to see either of these in practice too often. You'll see this one as just like a baseline. And so here are relatively real-world, quote-unquote, examples of AUCs. So over here we have an AUC of 90%, which is pretty good. And then we have an AUC of 65%, which is still better than the baseline. But this is not a fantastic model we're talking about, right? Yep. That is a good question. So to make sure I understand the question correctly, can we use the AUC as something while we are training the model itself? So based on my understanding, I would say no, because what we're doing is we're evaluating the model. To construct the ROC curve, we already have the decision rule at every possible threshold. And so I think bearing that in mind, trying to incorporate what the AUC would be into while you're training the model, that does not make sense to me off the top of my head. Yep. So what you can, it's so, right, so am I interpreting your question correctly in that you're asking that does a high AUC necessarily mean that let's say the probability we're predicting that belongs to a class is close to the true probability of it being that class? Or are you just saying that? Mhm. So what I can say is that a high AUC means that at least on the data you've kind of built this on, you're generally going to make the correct decision, right? But you don't necessarily want to think of it just in terms of like the actual probability because because it depends on the decision rules, right? Right. So one thing is that ROC curves aren't necessarily good for calibrating how good you are at coming up with the underlying probabilities. I don't know if that answers what you're looking for, but I'm happy to discuss this after lecture as well. So, okay, sounds good. So we've discussed why ROCs are great, but they do have their limitations, right? The one issue with ROCs is they are insensitive to class imbalance, right? Because if you look at what's going on in an ROC curve, you have the true positive rate, and then you have like the false positive rate, right? And so in the true positive rate, the denominator you're looking at is just like it's a proportion expressed out of all the actual positives in the data. And in comparison, your x-axis, your false positive rate, is expressed as, all the negatives in the data, right? But if you don't, but if you look at an ROC curve, like if you look at any of these curves, you can't tell me, or more accurately, I can't tell you what the underlying distribution of positives and the negatives in the data set is. Like this could be an imbalanced data set or not, but you can't tell based on an ROC curve or just based strictly on an AUC, right? Because like as long as you have plenty of decision points, so like this is you have a nice smooth curve, you can't actually tell if the class is imbalanced or not, right? And so we can use precision recall curves instead, which are sensitive to class imbalance. And as the name implies, precision recall is where you have like the model precision on the y-axis and then the model recall on the x-axis, right? And so precision and recall the formulae, right? So precision is true positive divided by true positives plus false positives, and then recall is the same as sensitivity, right? But in precision, because the denominator is true positives plus false positives, that means that we are now actually we are now interested in class imbalance because you're now looking at all the positive predictions your model made, right? So an earlier question was that why are sensitivity and recall, why are there two different terms for them if they're the same thing? And I said we talk about precision recall together and sensitivity specificity together, right? And the reason we have precision recall as one combination and sensitivity specificity as another combination is that you can diagnose or like quantitatively analyze class imbalance using precision recall, but not using sensitivity specificity, right? Because sensitivity and specificity are only expressed as proportions of like the actual labels or in the data, but precision and recall are also interested in like evaluating how your model does, are better diagnosing class imbalance, right? Because again, precision actually keeps track of, in the denominator, how many predictions you're making, not just whether they're correct or not, right? Like true positives and false positives. And so, yeah, we can use precision recall curves instead. And so the bonus too is that we actually managed to make it to the end of the lecture with enough time that we can go through this. So it says, the interview question I got asked was that, how do you explain precision and recall to the CEO? You may use the confusion matrix in your answer if you wish, but you're not required to do so. So spend like 3 or 4 minutes thinking about how you would explain this, and then we'll kind of go through like perhaps different student answers together, and maybe I can tell you what I answered. And again, remember that the idea is you're explaining it to a CEO, so you're not expecting to explain it to a highly technical audience. So yeah, take 3 or 4 minutes. Oh, yes. Oh, okay. So one thing I should have said earlier, by the way, is that you can only construct ROC curves for probabilistic models because it requires you having like decision rules for your different probabilities. So this is not directly related to the question, but I wanted to address that. You couldn't construct an ROC curve for an SVM, for example. Now, regarding the question is that could you come up with precision and recall curves for precision recall curves for multi-class classifications. So I think it just depends on if you can, how you define the metrics in the case where you have like multiple classes. Like something like recall, you could still define because it's just like, you could do like precision recall for like you could basically do this for a particular pair of classes, right? So you'd have like, if you had, let's say 3 classes, you could have precision recall where you're basically looking at class 1 versus not class 1. And then like class 2 versus not class 2 and class 3 versus not class 3. Because that's the easiest way, because then you can just define like a true positive as if you correctly predicted class 1 when it is class 1, and then like a false negative would be when it's class 1 but you predicted class 2 or 3 instead. So yeah, if I was asked how I'd use these curves in the context of multi-class classification, I'd basically just construct a bunch of like pairwise plots. Answer your question? Yeah. Lovely. Yep. Yeah, so I guess I may have gone through things a little quickly, but I did mention something similar, where the AUC of a classifier is equivalent to the probability that the classifier will rank a randomly chosen positive sample higher than a randomly chosen negative sample. And like just one way of kind of developing that intuition is that let's consider that where you have an AUC of like 100 or an AUC of 1, depending on your scale, then like if you have a randomly chosen like positive sample, so it like truly belongs to class 1 with a true positive rate of like 100 or perfect true positive rate, you're for sure going to like classify it such that your decision rule classified as a class 1, right? In comparison, if you have a randomly chosen negative sample and you're at this point where you have a false positive rate of 0, you also know it's not going to be a false positive, right? So it basically means it's going to be classified as a true negative. So the idea is that if an AUC has this characteristic, then it's going to assign like probability such that when you have your decision rule, the positive has a higher probability, and then the negative class has a lower probability, so your decision rule kind of correctly classifies them. So that's in the case of when you have an AUC of 1, so you know you're going to be right both ways. And then if you look at other AUCs, you can kind of extend that logic into thinking that, oh, an AUC of 0.9 is pretty good, so like this classifier generally does its job of classifying between the two classes. But there are clearly some examples where like you have some example below the threshold that's actually meant to be class 1, but your probability is below the threshold. And you probably have some examples where it's class 0, but the predicted probability is above your threshold, right? And so the AUC kind of quantifies the probability of that event happening, roughly. Does that help? Okay, lovely. And so it's 1:57, so any suggestions as to how we try answering this? Thank you. Yeah. Sounds good. Any other suggestions? Okay, it's 1:58, so I can tell you kind of how I approached it. So I didn't try coming up with the business situation on the spot. It would have been a good idea. I didn't do it. So I was just like, let's say, and so in fact, when I was asked this question, I was like told like the idea was that you'd use the confusion matrix, like that's what the question implied. And I asked, can I just like not use it? And the interview was like, I mean, sure. And so what I basically told the CEO is that let's have a situation where you have like 1,000 patients that are trying to see if they have COVID or not. And let's say 100 of them actually do have COVID, right? And so now, of those 1,000 people, you diagnose 10 people out of those 1,000 as having COVID, and it turns out all 10 of them do, right? And you tell the CEO, ta-da, of the 10 people I said, all 10 of them have COVID. CEO's like, but Ishan, there's like 90 people who have COVID who you didn't like diagnose. I was like, yeah. So I have a high precision model, but because I only got 10 out of 100 of the people who actually have COVID, it's a low recall model. And I was like, consider the case where instead we now have 1,000 people where, again, we have 1,000 patients. This time we have only 10 people who have COVID, and then we classify 100 people as having COVID. And of those 100 people, all 10 of the people who actually have COVID are classified as having COVID. So I'm like, ta-da, see, all the people who we said, of all the people who have COVID, we diagnosed them correctly. So, I got that 10 on 10. And CEO's like, but Ishan, there's like 90 people who don't have COVID. You said have COVID. I was like, yeah, that means I have a low precision model. And that is the gist of how I explained it. And then if you wanted to, you could also explicitly talk about why one might be better than the other, like precision versus recall, depending on your analysis. I didn't do that, but it doesn't hurt. And so we have just about managed to finish on time. So I apologize for rushing, but I guess it worked out. I will stick around for at least a while in this room answering any questions you have. Thank you for coming.